In this last video, we are going to analyze a simple sample of network address assignment. So let's assign network addresses in a scenario as the one illustrated in the figure, in which we have 3 routers and 4 subnets, as you can see, plus the 2 networks associated with the links that connect router 1 and 2 and router 1 and 3. Additionally, you can see we have the internet on the right, which would represent any other available network. But we don't have to assign any addresses there, of course. To do this, we have an available set of network addresses defined by 200.100.4.0/22. The requirements of this scenario are detailed on the right side. Subnet A1 has 60 hosts, A2 has 383 hosts, subnet A3 has 180, and A4 has 16. In all of them, we should also have one available address to be assigned to the router, because the router has an interface that belongs to each of these subnets. Moreover, we also have to assign addresses to the two subnets of the 2 links connecting the routers. That is, in between the routers we have some links, and those links also need some kind of subnet in there. In this type of scenarios, the simplest approach is to order the subnets from the biggest one, the one that needs to assign more addresses, to the smallest one. In this way, as we follow a specific order, we will easily generate valid network addresses. To start assigning each subnet address, we first need to define the mask value. That is, the number of zeros in the mask, as the number of zeros defines the size of the address set. More specifically, if we have n zeros, we will have a group of 2 to the power of n available addresses. If we start with the biggest subnet, we need at least 384 addresses, because we needed 383 plus the one of the router interface. This is covered by 2 to the power of 9, that is 512, which is translated into the mask /23, which has 9 zeros. In this first subnet, as the network address, we will use the lowest from all available ones, that is 200.100.4.0. As the mask is /23, the last available address will be 200.100.5.255, which represents the broadcast address. In between, we will have addresses ranging from .4.1 to .5.254, which are all the addresses that can be assigned to the host in subnet A2, because remember, this bigger subnet was subnet A2. The next available address is then 200.100.6.0, from which we will assign the next set of addresses, in this case for subnet A3, which is the second biggest one, which needs 181 addresses. In this case, the mask /24 provides a group of 256 addresses, which is enough. Therefore, the range goes in this case from 200.100.60 to 200.100.6.255, which is once again the broadcast address. Note that we could use bigger groups. For example, in this case, we could also use a /23 mask, okay? But that would waste an amount of addresses that other subnets might need. So we usually tend to use the smallest mask as possible, okay? So if we continue, in this case, the next available address would be 200.100.7.0. And we then follow the same approach. We calculate the optimal mask, which is, in this case, 26, as you can see here, because we need 61 addresses. And the next available address, which would then 200.100.7.64, as you can see here, okay, which will be used for the next subnet and so on. Note that we have two last subnets here, which require two addresses because we have one addresses per router interface. Remember that these two networks are associated with the links in these two connections, okay? We only need two addresses, but we also need the network and broadcast addresses, which makes a total of 4 addresses in the end, okay? So for having 4 addresses, we need at least a mask of /30, which could be somehow considered the minimum mask for any, let's say, logical network. Okay? As a conclusion, the network address assignment would look as illustrated in this figure. This is a good summary. Remember, this was the biggest, then subnet A3, then A1, A4, and finally the ones in the links. And once again, this is all so far. So thank you.